here? Remember? That could be precisely, no? The length that it will cross, for example, in this case, looks like a square, so all this will be L. Or in this direction, no? Also, it will be L. For simplicity, we could just write it as 1, make this a matrix of 1s and 0s. Okay. Here it is assumed, no, it is assumed that each pixel is the square of psi L. Just for a moment, right? Imagine that we have something like this. X, Y, and in this case, we have some setup like this, such that A, for example, will be some distance L here and 12. It's like a rectangle where the longer part is twice the shorter part. Something would change in our matrix or not in this case? Assuming that we have this measurement is in this direction in 1, in this direction in 2, in this direction in 3, and in this direction in 4. What would change? No? This is it for you to see the difference here? What would change in the matrix? In the matrix, would change only in M3 and M4 because here we have more distance. Right? So instead of only like L distance, now we have 2L and B also 2L. So for the row M3, we should have before, no? L times A plus L times B plus 0. No? But now, in this example, we have something like this 2L, 2L. And for M4, also same, right? C and D in the field. 2L, 2L. So you can construct your matrix in this way. In this kind of matrix. And this kind of matrix, right now we will try using what is known as iterative methods of algebraic constructions. Okay. The first one was this Gardner's algorithm. It's one of the algorithms to invert huge matrices. Is the invert each matrix is the Kasnav method. Developed 100 years ago. The technique as a mathematical tool, no? But then later, around 70s, they used it in the context of trying to understand that the tomography problem, the radon transform problem, is at the end of the day, construct a matrix like this and try to invert to obtain ABC. So the method of Katz-Marz is based on projections. The current solution is an iterative method, so it means that solution will start with some guess, some value that we think that may be value that makes sense, but then we will be updating it. That initial guess as current solution is projected in the hyperplane that corresponds to an equation of the system. The projections are alternated for different equations until the algorithm converges. Okay, this is clear for you or not so much? What's a hyperplane? It's like extension of the plane. A plane typically is thought as a, what's a plane? In space, what do we need to define a plane? Right, 3 points in 3D. In 3D, we need 3 points. And the 3 points we define a plane. In 2D, there is no plane in 2D. Oh, wait, maybe everything, but what you can think as a plane in 2D is one line. Okay, and one line is defined with 2 points. Okay. Yeah, so in the 3D domain, no, the 2D plane is the plane. And in the 2D domain, one line would be kind of the plane. But in 4D, on 5D, no, the dimension will be given by how many of these unknowns we have. No? Imagine we have like more pixels. 200 times 200 pixels, for example, we have around 40,000 pixels. So we have 40,000 of these A, B, C, D, and more variables. So we were talking about 40,000 dimensions. Obviously, something difficult to imagine. In this dimension, still we will have some equation of planes, no? Or hyperplanes. For example, 4D dimension. For example, no? What would be in a 3D equation of a plane? For example, 2x plus 3y minus z equal 1, for example. This is the equation of one plane, right? You only know some coefficient x, y, z, and some constant, some parameter on the right. No? That defines a plane. And you can plot that, right? In 3D, you know? Just make, for example, x, y, 0, and see the intersection in z. No? Or make y and z 0 and see the intersection x, no? And x is 0 and see the intersection y. No? You can get your 3 points and you can more or less draw the plane. But in 4 dimensions, for example, like in this case, 2a plus 3b minus c plus 4d equal 10. This will represent you see that plane in 4 dimensions. In this case, dimensions A, B, C, D. Do not use X, Y, Z. Obviously, this is more difficult to imagine, right? Because you need to set 3 points to 0 and calculate what is the other. Right? But graphically, maybe I don't know how to imagine that. Mathematically, it's use an extension for variables. So this is hyperplane. So we need to project our current solution in the hyperplane. The projections are alternated for different equations until the algorithm converges. So, and there is one example here in 2 dimensions, is to try to see the nature of the algorithm. I mentioned that in 2 dimensions, the equation will be, for example, 4x minus 3y equals 7. For example, this a line. Maybe other equation could be x plus y equal 5, for example. For this, imagine that we have 2 variables and 2 equations. That's a problem that can be solved. X minus solve this with two variables, it will be easy, right? What we can do? Yeah, that's a good idea, right? You can multiply by 3. That's why this will be 3x plus 3y equals 15. And then sum that, right? And you will have 7x equals 7 plus 15, 22. Okay, I will change this to make it equal to 6, so that we have 21. That way, x will be 3. And knowing one, you get the other, right? If x is 3, no, y need to be 2, right? Okay, so this is the solution. In fact, no, we can try to, given that we are in this example, can we plot these curves in this draw? What would be 4x minus 3y equals 6? These are things that maybe you have seen on the past a little bit, right? So it's good to remember that, okay? So how can we plot this curve? Could be like, for example, in this curve, if x equals 0, then we need what? We need, if x equals 0, it means that y should be how much? Minus 2, right? If y is 0, how much would be x? 1.5. Okay, so we have 2 points for this. x0, y minus 2. So x0, y minus 2. Y0, x 1.5. So 1.5 is around here when I equals 0. So it means that the curve will be, the line in this case, the line will be this. Okay, good. The other is x plus y equals 5. How is the line in this case? No, again, if it's 0, y is 5, right? If y is 0, x should be 5 too. So it means 5 is around here, right? 5 is around here. So it will be something like this, right? Yeah. Something like this. And then the method here is, well, we try. Well, first of all, can you guess what are the coordinates of this point? What are the coordinates of this? 3, 2? 3, 2? Why? Hands. How are the coordinates of this? It is not clear for you that the intersection should be the solution that we just found? Okay, if it's not clear, okay, review your material, previous course about equation of lines and this. Okay, of course, it should be 3, 2, right? That's precisely what the solution of two equations mean, right? The solution of two equations means find this point, no? This point of intersection. It's a point that is valid for both equations, right? And that's exactly the solution of these two equation system. That. Okay. So the method is, okay, in two equations is not so difficult, we just did it, but in a more complicated case, I mean 3D, we will have, instead of lines, planes, right? 3 planes in the space. So how we can solve that? We can maybe create our matrix of 3 equations and try to do this method Gauss something, right? You remember? Gauss elimination or Gauss So Jordan, I think the name, right? It was made that version of methods of solution of the equation. In 4D, yeah, that's more complicated. But in 5D, even more complicated. Okay, so this method, what this method is going to do is, okay, imagine that in a more complicated case, 4D, 5D case, we don't know the solution. We don't know the 2.3. We don't know yet that. Like in this case, right? We have two lines that correspond to two equations. And we don't know these points. So the problem starts with, okay, just write some guess, some points in this domain. Start with some point, x0, y0, some initial guess. And then calculate the projection of this point in one of the equations, in one of the lines or planes or hyperplane, depending on how many variables you have. Just make a projection. And in this case, the projection is just something like this, such that this is 90 degrees. Right? This is projection. So this point will give some, like a second on one update of the solution. Instead of x0, y0, we will get x1, y1 at this point. And then, what else? Do the projection into the other equation. Such that this is 90 degrees one more time, and this point will be x2, y2. Okay? So, notice, right, we want to find this intersection, this point, the coordinates of this point. But only after two iterations, we are 1, 2. It's like this method with two iterations. Okay, maybe we are closer to this from here than here, but we still not that yet. What else can be done then? Continue, right? Do that again. Now let's project this. No, if we run out of the equation, okay, let's start with the first one. And then project to the first equation. And then project again. And then project again. And then project again. And you see that eventually, we will be very close to the solution. Okay? And the thing is that to obtain this projection, we don't need to calculate the inversion of a matrix, things like that. The projection, we need only the equation right here. How can we get this projection? x1, y1. Right? That's Kurzman algorithm. I think the next slide is. In the 70s, the required number of floating point operations was very high. A raw approximation consists of making the elements of the matrix to be L or 0, whether the rate passed by them or not. Okay, so we need. This is saying that this algorithm can smart make possible solution by iterating many times. And this algorithm also saying that, for example, imagine that we have something like this, 4 pixels by 4 pixels, 4 by 4 pixels, 16 pixels. So we have one ray that crosses this, and let's say this A, B, C, D. This equation will be how much? Similar here. And 5 variables, so we call it in a more organized way, like A11, A12, A13. No, it's just saying, okay, every picture we have no row and column, row, column, row, column. So in this case, no, our problem will have how many variables or unknowns? How many variables? 16, right? No, assuming that these are the unknowns, no? Yeah, we will have very long vector here. 16. Okay, so let's write it row by row. So the first one will be A11, A12, A13, A14, A21, A22. Okay, I will just put it like this until we reach the last one. And how many equations we have in this case? The equations will be given by this measurement. It's N1, N2, N3, N4. So we'll have, in fact, less N1, N2, N3, until N8. So this vector is 16 times 1. This vector is 8 times 1. So it means the matrix that will convert these unknowns to these measurements. What is the size of that matrix? What should be the size? How many rows or columns should have? Mm-hmm. 8 times 16. Remember that for having a matrix product that makes sense, this should be here, right? And eventually this will be here, and this will be here. Which makes sense because the product of matrix vector at the end is like this row multiplied by this column, and this will give the first. And the second row multiplied by this column, and will give the second. And so on. So in this problem, what are the coefficients here? Well, for M1, only these 4 contribute. So we'll have, if we have this order, it means will be L, 0, 0, and the rest. For the second, M2, how is this going to be? The one that contribute are to 1, to 2, to 3, to 4, right? So these 4 didn't contribute, so we can have 4 zeros initially. But then the next ones will have 4 S there. And then zeros. Okay, so you can construct your matrix always, right? It's just try to be organized. And obviously in this case, for example, it's also important that the solution will be maybe not perfect because we have more equations, less equations than variables, right? And the general rule is that you should have at least same number of equations than variables. And if we have more equations than variables, what happens? I think this is square. I remember that we talked a little bit in the first class. We can have the approximate solution with the least squares. Okay, and this, in this slide is saying that maybe you can have another direction, right? So something like this. One ray in this direction. Let's call it M9 or this M10. And you can have many directions, not only this perpendicular, horizontal or vertical. Okay, let's think about M9, for example. Okay, we have M9, so one more equation. then the question, what would be? No? It would be some length in this case I will make it that it cross the diagonal, so 1L in this pixel, 1L in this pixel, 1L and 1L here, right? So it should be L in 1, 1, L1, 2, 2, L3, L4, 4, right? But no, right? Because the distance is a little bit larger, right? So it should be L root square of 2, right? If we want to be precise. Sometimes, no, in the past, they say, okay, no, just put L. If it cross L, because maybe you can have some ray like this, no? So then you need to calculate exactly this, and this, and this, and this, no? It's a little bit difficult, tedious to do that calculation geometrically. So some people say, okay, in the past, like, oh yes, if you see that it cross, just put 1, no? There. That's it. Both are okay. I mean, if you explain the reason why you're doing that. Mm-hmm. Okay, what else? So, in this ART algorithm, el delegado me había preguntado si el quiz puede ser a las 9:30. Ya, sí, no hay problema. Puede ser a las 9:30 esta vez. ¿Le avisan de repente el delegado porque no lo veo por aquí? Okay, and the next thing is, okay, we have many hyperplanes, many equations, no? Again, no? One more time. This, writing this times this is like having an equation of dimension 16. Right? So that's why hyperplanes. Okay, so how is the procedure of updating the solution, no? With the CAD Smart, no? Trying to project the hyperplanes, no? And trying to update that gets a solution, that possible intersection value. Okay, the solution will be an update, no? F in a moment n plus 1. Okay, this n plus 1 refers to the iterative moment. No? Like solution 2 will depend on the solution 1, or the solution 1 will depend on the first guess, no? F0. Okay, so this n represents here the iterative point, no? The iterative moment. Obviously, then the solution updated will be the first solution plus something. Okay, and that something is given by the product of delta gi, yeah, times a vector of ones. Okay, this is a vector of ones. Like, you know, we don't have here L, no, and just as I mentioned, think about ones, no, if it goes or not. These are kind of the vector of ones. There's some one vector like that. Multiply by delta gi. What is delta gi? Delta gi will be gi minus n, the length can be 1, and multiply by this. That in this case represents the. No, can you have a guess? What is this? Is a product, okay? It's a product of a vector of ones and the current solution, okay? The current solution. The vector of ones, no, is the is ray. In this case, the is ray is, no, the first ray, second ray, third ray. No? It's like, again, one more time, this kind of vector of 1. No? The first, second, third, no? In the order that we are trying to choose. So this vector of 1 refers to this. And that vector of 1 is made by ones or zeros. No? It's 1 if the iésimo rayo, no, pass by the késimo fixed. No? It's exactly what we have done. Right? We say, if, for example, M1, this ray crosses these two, and in this form, there will be 4 ones, no? And the rest will be 0. So that, don't be confused by the nomenclature. No? It's just saying that this, oh, we are talking here about vector of 1s and 0s. Okay, so we make this. What's this? The symbols. Muy bien. El producto del vector, ¿no? Este vector de unos, de ceros, estamos diciendo, por la solución actual, ¿no? Muchas veces. In which way they will multiply? Which kind of product is this? It's an inner product. What is an inner product? You studied it, right? You take a class on linear systems, something like that. The linear product, for example, for the vector, in mind we have the vector 2, 1 and the vector 3, 2. What is the linear product of these two? Is the first element multiplied by the first element plus the second element multiplied by the second element, right? Like this is vector A and this vector B. No, it's 2 times 3 plus 1 times 2. In a more mathematical way, this is writing as A transpose B. No? That in that way we will have a row vector that multiplies column vector. And the product of a row by a column, what is the size of this? No? It's one number, only one escalon. It's not a vector, it's only one value that will be exactly this. Okay, so this kind of typical nomenclature for the inner product. No? Okay, so this is a number. These are vectors, yes. Like 1 and 0s, or the current solution that is also a vector, no? Of value that we will get for the intersection point. But the inner product is a number. And then there will be this delta GI, that is GI minus L times the inner product. And here GI will be, or G will be this vector, okay? The vector of the measurements. The vector of the measurement that we are saying like this. Okay. So G1 will be the value of measurement for the first ray. No? G2 will be the ratio for the second ray. And third ray and so on. It's basically this. No? Maybe I could have used the variable to be here, but this G will refer to that, to the measurement in all the, every ray, V1, V2, V3, and so on. So for the field ray, one more time, what we are going to do, we will subtract the current measurement minus the inner product of that first ray. No? We're talking about the first ray, the 1, 0 vector of the first ray multiplied by the current solution. That will make a delta G, like a distance, discrepancy between the current solution and that plane. And that distance will be used to approximate the solution to that plane precisely. So this is like a vector. This vector is the current solution. remember. Here we have some solution, and let's say this is the first one, G1, and this is G2. If this is the first solution, we need, no, we can think this as a vector, so we need to calculate this vector, the vector that is, no, perpendicular to this first hyperplane, first line. The direction of this vector, in fact, is given by by this 1, 0, vector. So we just need to say, okay, from this point, how much we need to move to this position, and that movement precisely is given by delta G. And then we will obtain this one. And that will be the next solution. Okay, so we have this delta G multiplied by vector of ones and divided by L and I. And L and I here is and I how many vectors different than one are here. Okay, in this 1, 0 vector, for every ray we will have a number of ones. The number of ones is basically Ni. Ni is the number of ones in that individual vector. Okay. We'll do one example in a moment. Okay. Physical interpretation of ART is straightforward. For each ray, the error in the projection based on the current estimate of the attenuation is calculated. The error is divided by the total distance crossed by the ray, and the error average is distributed equitably in all the pixels in the path of the ray. This algorithm is then of the class projection back projection. Okay, so imagine that we have this configuration, very simple as 4 pixels. And we know already the value, okay? We know already how much is the attenuation in A, B, C, D. We know the attenuation of A, B, C, D. Imagine that we had this configuration. Like a real configuration. ABCD has this attenuation. It means the attenuation is 1, 1, 3. No, sorry, 1, 2, 3, 1. In this case, if we take measurements M1, M2, M3 and M4 using the Kaufman interpretation. No, more than that. What is the measurement of M1? How much would be M1? Let's assume that the length here are R1, okay? On the length of the square. How much would be the first measurement, M1? Paco. What do you think? Correct? Three. Por uno, por uno. And two? How much? C más D. And three? 4. Y en 4? Could be 2. Could be 2. But here we are not doing the inversion yet. We are just doing the calculation of M4. So if we know exactly the crossing direction, we can say that okay, this is 2 raised to the square of 2, just to make it be more accurate. Okay. So this is the real, okay, the real value. But then the question is, how can we imagine we know only this, and from this we want to calculate the values of ABCD, no? These values. How can we do that? We need to do the Kaufman algorithm. What is the first step of Kaufman algorithm? César. La fórmula anterior, pero antes de la fórmula, ¿qué tenemos que hacer? ¿Qué es lo primero que tenemos que hacer?
La matriz.
Correcto, ¿no? Intentar hacer la matriz. Si no hay matriz, ¿qué cosa vamos a resolver? No matriz, ¿no? Let's have 4 unknowns. And the measurements. And 1, and 2, and 3. Just to make similar to the Kaufman algorithm, I'm going to call it J1. Okay? J1, J2, J4, and J3. Exactly the same. This is another variable. And these measurements are known. We know before that is 3, and 4, 4, and 2 root square of 2. Is 4. 2, 0, 0. ¿Podría ser? ¿Qué determina esto? ¿No? Determina la longitud, ¿no? Aunque, sí, aquí es como que sabemos que tiene 2, ¿no? De repente se confunde un poco para pensar que va a ser 2, pero no, ¿no? Realmente los valores aquí son solamente las longitudes, por longitudes ahí en este caso será 1, 1. Para la segunda, para G2, que sería esta.
0, 0, 1.
0, 0, 1. Para la tercera. 1, 0. Y para la cuarta.
1, 0, 0.
1, 0, 0, 1. Si somos Classman algorithm, ¿no? Aquí sí se hace una guía. Hasta de cruce le ponemos 1, no cruce le ponemos 0. Ok, ese es el primer paso, ¿no? Armar nuestra matriz. Y el siguiente paso, ¿cuál sería? Digamos que queremos, ¿no?, usar las 4 ecuaciones, ¿no?, una vuelta entera, e intentar derivar, ¿no?, A, B, C. ¿Qué necesitamos ahora? ¿No? Usar el algoritmo iterativo. To use, ¿no?, the iterative algorithm to update something, right? Update a solution. What would be the first solution? What would you choose for the first solution? In fact, it can be anything, okay? Just for, in my case, I will choose, for example, the solution 1, 1, 1. I will assume that everyone has the same value. If I give you that information, no problem, okay, you can use that. If I don't give you nothing, maybe you should guess some value. Okay, so the first solution will be I will try still, okay? And I will say, okay, my first guess is like everyone is the same, and the same to 1. Imagine that I give you this to you. Okay, this is the first solution. What else do we need to do? Define a second solution over this is the zero solution, initial. So the first update will be how much? No? Will be the initial guess plus delta gi multiplied by lni and vectors of 1I. But what is I here? What is I here? It refers to what? What is I in general here in the context of this? I refer to the rays, right? First ray, second ray, third ray, fourth ray. Okay. And the rays are basically this vector. So you should notice that for the first equation, actually no, it's like instead of I, we're gonna write I1. What is the vectors of 1? Mm-hmm. 1, 1, 0, 0. What is L? Well, in this case, I will use L equal 1, okay, for everything. So it's L equal 1. What is Ni? N1, no, in this case. We are talking about the first ray. So only we need this, right? Delta G1. And delta G1 should be G1 minus L, that is 1. And the inner product of 1, 1, and F 0. Like the first solution, the first guess that we have. Okay, how much is G1? Mm-hmm. 3. How much is this product? 2? I will write it one time. Right? Okay. This is the vector, no? 1, 1, 0, 0. That corresponds to that first ray. Multiply by our first guess, right? We said our first guess is this. How much is this? So this is 1. Our first delta G is 1. So it means we are here. The first guess is 1, 1 plus delta G 1. How much is delta G 1? Multiply by what is this? 1, 1, 0, 0. Used to this to make sense. I think this symbol corresponds to transpose in this case, like coordinate. Okay, I will write here like, in a column form. Okay, just to make sense with the dimensions. L is 1 and N1 is 2. Right? Yes, okay, so this is the first update. The first update will be how much? This is 0.5, right? So 0.5 and multiply this and then add it to here. Something like this, right? Right? No, I think I. 1, 1. Right? Okay, second. Yeah, this is the first update. Okay. This would be our F1. First update. The second update. What do we need? Well, we need the first update, no? Like not the zero update. Okay? The one that you use calculate. Plus what? Delta G corresponding to the second vector of ones divided by L, number of zeros, number of ones, in that, multiplied by the vector of 2. Okay? How much is, no, so let's try to calculate it, right? L is 1, and 2 is, how much? 2, right? The vector of ones for the second row, for the second ray is 1, 0, 0, 1, 1. Delta G2, how much? Maybe we can write it, no? This time. It's going to be translating, right? The vector of ones is the product with the current solution. So G2, how much is it? 4, right? 4 minus 0, 0, 1, 1. Inner product 1.5. How much is this? 2, right? So 4 minus 2. So here, okay, we have 1.5, 1.5, 1, 1, the previous solution plus delta U2 that we use to calculate that is a number, no? It's 2 divided by L and 2, that is 1, 2. Multiply by the vector, right? The vector of 1 zeros for the second row. That would be this will be I think this part it won't change, right? It's 1.5. the series update would be how much? Would be the previous update, right? What is the previous update? 1.5, 2 plus delta G3 divided by L, that is 1, and N2. No, for the field rate it grows also 2, right? You can see here. This multiplied by the vector of 1, 0, 1, 0. Right? So only need to calculate delta G3. Delta G3, how much is it? This, no, G3 minus minus this, no? Multiply by what? By the first solution, no, the current solution, no? By this solution, right? How much is this multiplied by this current solution? 3.5, right? So this could be 0.5. So we have here 0.5. Right? So how much it would be? 0.5 divided by 2? 0.35, right? 2, right? Two. And the last one, okay? The last should be the previous. Huh? So we will write it. Plus delta D4 in this case divided by L1. And how many ones, no, it draws that force? Also 2, right? Multiply by what? By the vector of what corresponding to that last row. And try to notice here, right? When I write, for example, in this way, like I say, when it's 0, it doesn't matter, right? This, whatever is here multiplied by 0 will be 0. So it's like the one that has 0 won't change, right? It's like this row, this ray doesn't have effect on the pixel that have 0. So just have to keep that in mind. But for the other vector, not for this one and this one, yeah, it will have some effect. How much is delta G4? 2.8. Minus no, the inner product, right? And that is the inner product of the vector of ones and the current solution, right? What is the inner product of the vector of ones and the current solution? 3.75, right? So this should be almost minus 0. Oh, 1.05?
No.
¿Seguro? No es esto. Ah. here, it should be replacing, right? Minus 0.95. And this, how much? Approximately minus 0.47. 48, 47. And then, what will we have? No, this minus 0.47 will be multiplying here and here, right? It's like 1.75 minus 0.47. These two won't change, right? Something that we also notice. And the last one. Okay. Okay, there. Usually I will write it like one decimal only, like around to one decimal. So this is our solution of class math in the first round of updates. On what it was the solution, the real solution, like the actual values of ABCD. No? I think it's there, right? We should try to obtain 1, 2, 3, 1, right? And notice that we start with 1, 1, 1, 1, right? Like no difference, right? We say, okay, no difference in the middle. But now we obtain that, no? Especially the fifth pixel now is starting to being larger, right, than the others after this update. Which kind of makes sense, right? Because also the fifth pixel is larger in the original. Okay, one is small, but yeah, okay. Maybe there are some changes still that with a second update can be done, right? Yeah, and you're going to repeat this process. No? In fact, that's what it was done in the past, right? Repeat this many times. I notice that operations are very simple. It's multiplication of vector with vector, right? Product, sum, nothing too complicated. No, and only with one row we are close, right? It won't be perfect, right? Because remember when we have like two lines like this, right? If we start here, using the equation once and then the other equation once, we are getting here, right? It's not, it doesn't mean that we are getting the solution in only one round, right, of using the two equations. So, yeah, okay, that is not perfect. Okay. You can just also calculate, no? What is the error right now? If we say, okay, this is the initial solution and this is the solution here. Or in fact, no, at any moment, no, you can calculate the error with respect to this vector. How can we calculate that error? You can subtract, right? For example, here, no? What is the difference between these two? The difference is 0.3 minus 0.5 minus 0.7 minus 0.0. No? And you have this vector of differences, and then how can we calculate like the error? Could be, for example, the norm 2 of this, right? The norm 2. What is the norm 2? The root square of all the elements squared. For example, maybe will be one way to say how far we are right now from the correct solution, right? This relative to the norm of this, for example. Okay. Continue. So one way of solving this Radon inversion is with this Kaczmar's algorithm. Other way is performing a reconstruction in the frequency domain. That this will be closer, or this will try to relate more the Radon transform concept with a concept that you know very well, no? That is the Fourier transform. That will be another way to try to solve the inversion. Alternatively, the reconstruction can be performed in the frequency domain. Researchers in nuclear tomography have reported an analytical relation between the Fourier transform of the projections and the function to be reconstructed. Okay, so this plot is saying that we have one object with some distribution of attenuation. We have many rays that reach that projection domain, and we will have a curve. The curve will be, typically we use the variable p, and not this like G, angle theta, and then this could be the projection. It means the attenuation across this path may be larger, and the attenuation here may be lower. Okay, so always you can get these projections, and if we get projections from all the angles, we have many curves, and then if we put together many curves, that's the image of radon transform of the sinogram. Okay, so at some point, one person say, okay, what happened? What happened if we take the Fourier transform in one dimension of this curve? What happens if we take the Fourier transform in domain P of this curve?
Mucho tiempo ahí
and what is obtained after taking the Fourier transform of this curve will be part of the information of the Fourier transform in two dimensions. Let's say that this medium is fxy. Fxy is this structure, this geometry with some values inside. And fxy in two dimensions, the Fourier transform will be something like this. Right? We use nomenclature SUV. You know how to calculate it, right? At least the definition, I hope. No? If we know SUV, it's possible to obtain fxy. No? If we know fxy, we don't obtain SUV. So what the Fourier transform, this frequency domain approach of the radon transform inversion we try to do is to obtain information about FUV with the projection. So we obtain information about FUV with the projection. And the first projection, for example in this case, this first projection, if we take the Fourier transform in one dimension, because this is a line, a curve, we will obtain the values of the Fourier transform across this line. The sample points across this line. And of course, that's not all. In fact, if we obtain FUV, but for some points of U and V, for some coordinates, that will be casually, across this line that has also the angle theta that we have in the projection. Okay. Okay, so that's the main idea. The Fourier transform in one dimension of the projection will give us some information about the 2D Fourier transform of the original function fxy. Okay, but this information is not all FUV. What else can we do to obtain more information than only these points? what else can be done? You remember that this is one projection in the angle theta, but angle theta will be changing. For example, if we change to bigger value of theta, we will have information across this line. Okay? Across this line. Samples at some point. And if we change theta, we will obtain information across these lines. And then we can repeat that. Repeat that for basically all the angles of theta. Trying to cross this and yeah, what is done is actually take this for many angles of theta, not only one, several, and then we have almost a complete coverage of the Fourier domain, SUV. So we have samples for many points in all this area, and that is. That is what it helps, right? We obtain an estimate of FUV. And when we have the samples FUV here, what else we can do? Well, take the inverse Fourier transform in 2 dimensions of FUV to obtain FUV. That's it. To be the linear point Fy, we have some projection, Gt in angle theta. What will be the Fourier transform of Gt theta? For Gt theta, we will create a Fourier transform Gq theta. It's like for this spatial variable, we have the frequency variable Q. The angle is the same. And typically the nomenclature, if you use G like this, you will use capital G for the Fourier domain. Okay, so the 1D Fourier transform of G theta is this. The 2D Fourier transform of Fxy is FUV. So what is which samples we can obtain from FUV using G theta Q? And the samples that we can obtain from FUV are the samples that have this property, such that UV are the form. UV is from Q cosine theta and V is Q sine theta. Or in other words, V divided by U is the tangent of theta. So it means that the sample will be across this line that represents the tangent of theta. Okay. And this is kind of a demonstration, so let's see some of these equations. From the definition of the 1D Fourier transform is the integral from minus infinity to infinity of the function multiplied by complex exponential e power minus j to 5 pq or tf. Maybe you're familiar with the variables time and frequency in that form, but it's just similar. So it is 1D. And then, basically, the definition of the G theta, the Radon transform, the projection, is replaced here by this expression. That is the definition that we saw last week. Where we have an integral across the domain of a function p cosine theta minus p sine theta plus p cosine theta. So it represents the cross points in fxy for this value of p. Okay, so some change of variables are done here. PT, well, basically, all this, we call this A. And T sine theta plus T cosine theta, we call B. This is equivalent to write, like AB is the product of cosine minus sine, sine cosine of T. Change variable there.
Porque me pareció ahorita caída. Ya vendrá. Something like that, replacing A and B here. A and B, we obtain this. And we need to replace here again. P is how much? If we're going to write this like this, cosine theta minus sine theta. How can we obtain PT? No, it's going to be the inverse of this line design. The inverse of this. The inverse of this was how? Remember, interchange, no? These two. And the negative sign of these two. Sine theta. Something like this. And the determinant of this one, that's why I didn't write it. So it should be A cosine plus B sine. Okay. So they write this way. And also dA dV, the differential terms of dA dV will be the same as dP dt. Okay, I will leave this here. And there is a proof. In fact, here is the determinant of the Jacobian of AB with respect to PT.
No, it's a differential, no? A with respect to P, differential A with respect to T, and take the determinant. That will be 1. That's why not here. Okay, so replacing this, we obtain this part. We obtain this part. So basically, it has the form, the form of the 2D Fourier transform, f xy, dxy, and here xy. If we are more familiar with this nomenclature. The only difference here, that we don't have u and v. If it was u and v, ux, vy, it will be the definition that we know very well, the 2D Fourier transform. But here you have this, q cosine theta plus q sine theta. It means that this is not a general form of the 2D Fourier transform, but only the Fourier transform in a specific uv value. And that specific uv value will be u q cosine theta and v q sine theta. So that's why. Again, the Fourier transform of the projection will be one slice or one line of one portion of the Fourier transform in 2 dimensions. Therefore, obtaining projections at different orientation angles allows obtaining lines from the 2D transform of the image. It's something like this, right? The samples that we obtain are given by these points for different angles. And the problem is that the samples in Fourier space, in UV, are in a polar grid, in a non-Cartesian grid. It's like a polar form, right? But for FUV, ideally we would like to have a Cartesian coordinate, like values like this. Yeah, same in this animation. But here more like a polar. No? Near the center are a lot of samples, but outside, not too many samples. So we can try to interpolate to obtain more samples in a grid, from polar to Cartesian grid, to make positions, do an interpolation. But one more time, the high frequency, large values of AUV, there is not enough information of samples. Okay. Then the solution will be just using the next, after noticing that this relation between 1D Fourier transform and 2D Fourier transform, eventually we want to obtain, right? This in fact is the definition, y is FUV multiplied by this. What we can do in this case, knowing that we don't know UV for a Cartesian coordinate, we know UV for this more polar coordinate. So we need to do a change of value. Okay, I think I can do this next week. Just to have time for the quiz. Any questions? Ok, entonces comenzamos el quiz en un ratito. Vayan sacando una hoja.